The mandated application of surrender paint transformed a high-speed twin-engine reconnaissance platform into a premier historical artifact. Yet the aircraft's geometry imposed an immediate operational constraint that would shape every recovery decision that followed. This is the technical investigation of a Mitsubishi Ki-46-II, designated by Allied intelligence as the Dinah, bearing the precise serial number 2783. Operated by the Imperial Japanese Army Air Force, this specific aircraft represented one of the very last airworthy machines remaining at Vunakanau airfield at the conclusion of the Second World War. Prior to its final dispatch, the aircraft underwent a mandatory and permanent visual alteration. Allied surrender protocols dictated a strict evidence signature to prevent accidental engagements. The original operational camouflage of the stressed skin airframe was entirely painted over with a heavy overall white finish. Large green crosses were applied to the wings and fuselage, visibly marking the airframe as surrendered rather than a combatant. It was the required recognition code for Allied pilots and ground observers. Without it, the transit could have been misidentified and treated as hostile. The mere fact that serial number 2783 could still start its twin radial engines was a result of intense logistical discipline under a prolonged condition of severe maintenance starvation. Japanese ground crews at the isolated Vunakanau airfield operated under a total and uncompromising embargo on factory replacement parts. Continuous Allied bombardment had completely severed maritime supply lines. This forced the remaining mechanics to cannibalize destroyed airframes and improvise critical repairs just to maintain baseline flight systems. The engineering reality of keeping a complex aerodynamic monoplane airworthy in a highly corrosive equatorial climate without a functioning supply chain required ruthless prioritization. Ground crews had to strip non-essential structural components, focusing their remaining resources entirely on engine compression, control cable tension, and fuel delivery manifolds. Every hour of engine runtime consumed irreplaceable components. On September 18, 1945, this meticulously maintained but starving aircraft initiated its final commanded flight. The procedural flight path covered a mapped distance of approximately 100 miles. For transiting from the secured ramp at Vunakanau to the designated Allied receiving perimeter at Jacquinot Bay airfield. The Dinah did not execute this transit alone. It was accompanied by 3 A6M0 fighters, also carrying surrender markings. To enforce the transit corridor and ensure compliance, Royal New Zealand Air Force F-4U Corsair fighters escorted the formation in overwatch, ready to intercept any deviation from the filed flight plan. The airborne phase of the transit proceeded exactly according to the strict constraints of the protocol. The aircraft successfully traversed the dense tropical canopy and coastline without suffering engine failure, manifold fires, or control surface lockup. That absence of failure was the only proof of the ground crew's work that mattered now. With the identification accepted, as the formation pressed on. As the formation approached the airspace over Jacquinot Bay, the operational objective was strictly defined. The crew was ordered to land, decelerate on the runway, and formally turn the fully functional airframe over to waiting Allied inspection teams. The Japanese crew aligned the fast, aerodynamic twin-engine aircraft with the Jacquinot Bay strip, but one mechanical threshold at touchdown would immobilize it for good, an operational paradox that defines its final flight. Allied engineering teams assessing surrendered aircraft operated under a rigid maritime cargo deficit that forced a binary selection between preserving intact airframes or harvesting concentrated technical intelligence. The physical reality of this logistical calculation materialized the moment the twin-engine aircraft touched down. So upon making contact with the runway at Jacquinot Bay, the Mitsubishi suffered an undercarriage mishap on rollout. Contemporary accounts describe a burst main wheel tire and damage to a main landing gear leg that slewed the aircraft off the runway during deceleration. The Dinah came to rest largely intact but immobilized, unable to taxi out under its own power or be readied for another flight. To reopen the strip, recovery personnel cleared the aircraft to the perimeter with a tow, leaving the kind of scraping and local skin distortion consistent with a disabled airframe being moved without fully serviceable landing gear. Once the wreckage was pulled to the operational perimeter, Royal New Zealand Air Force personnel evaluated the disabled machine for transport as a secured artifact. Maritime shipping decisions were dictated by geometry. The airframe measured exactly 36 feet 1 and 1/8 inches in overall length, and the monolithic cantilevered wing spanned 48 feet 2 3/4 inches. With ships prioritized for repatriation and essential stores, the aircraft's cubic volume exceeded the available hold dimensions and deck space on the transports at hand. Furthermore, the unbroken structural envelope of the Mitsubishi wing could be dismantled in theory, but doing so at a forward strip demanded time, manpower, lifting gear, and proper support jigs that the base could not easily spare. With maritime lift dominated by repatriation and essential stores, the engineers shifted to a volume-based triage and selected only components that could realistically be shipped. The engineers formulated a strict component harvesting protocol focused on removable, high-density technology centered on the power plants. The two engines and their propeller assemblies were removed, reducing the shipping footprint to something that could actually be manifested and carried. Multiple later accounts record that these compact propulsion units ultimately ended up in New Zealand for technical evaluation. The deliberate harvesting operation preserved the critical propulsion technology, while the remaining fuselage, tail empennage, and center wing structure were judged too bulky for priority transport and deemed dead logistical weight. With the runway cleared and the engines removed, the remaining stripped structure required no sustained preservation effort by Allied forces. The hollowed airframe was left on the margins of the operational area until it slipped beyond any practical recovery program. What happens when a structurally compromised, thin-skinned aluminum shell is left exposed to the aggressive biological and chemical degradation of a remote equatorial climate becomes a matter of slow, unavoidable environmental physics. Exactly 36 years separated the wartime abandonment of the airframe from the first dedicated physical wreck survey. In 1981, aviation wreck investigator Brian Bennett traveled to the Jacquinot Bay area to locate and evaluate what remained. In the intervening years, the equatorial jungle had consumed the margins of the airstrip and obscured the surviving structure. Instead of sitting as a pristine time capsule, the wreckage had endured years of exposure and, according to later accounts, periods of stripping and movement around the airfield perimeter, complicating any claim of a single, unchanged resting point. Locating the wings required intensive manual clearing through dense brush just to expose the external geometry of the site. Upon uncovering the primary structure, Bennett conducted a thorough site evaluation to determine exactly what survived the jungle. The survey confirmed the 1945 triage. Both power plants were gone. The structural inspection of the forward wing sections revealed the precise methodology of the component harvesting operation. The heavy engine mounts were cleanly unbolted, while hydraulic lines, fuel manifolds, and control cables were deliberately severed at the firewall bulkheads. This procedural detachment of the high-value intelligence items from the low-value bulk structure defined the exact footprint of the remaining wreckage. By successfully isolating and removing the two engines decades earlier, the initial military engineers had inadvertently left massive open structural wounds across the aerodynamic envelope. Without the large radial engines sealing the forward nacelles, the delicate internal wing ribs, fuselage bulkheads, and unpainted internal skins were directly exposed to the constant tropical rainfall and continuous ground moisture. This open exposure initiated a relentless and highly destructive process of galvanic tropical degradation. The humid jungle environment created a continuous blanket of moisture over the wreckage. As the dense organic overgrowth trapped wet soil and rotting vegetation against the airframe, the heavy overall white surrender paint and the original factory protective coatings eventually failed. When dissimilar metals within the aircraft construction, such as high carbon steel mounting brackets and thin stressed skin aluminum, were bridged by highly humid rainwater, an electrochemical reaction occurred. This constant electrolyte exposure caused the thinner structural aluminum to rapidly oxidize and dissolve, specifically targeting the rivet lines, wing roots, and lower fuselage junction points. The environmental physics fundamentally altered the integrity of the wreckage. The aircraft transitioned from a rigid, load-bearing vehicle into an extremely fragile and brittle metallic shell. The survey confirmed that the lowest sections of the fuselage, which rested directly against the damp equatorial soil for 36 years, had suffered catastrophic material loss. Whole sections of the belly skin had corroded entirely away, leaving the heavy internal spars completely unsupported from beneath. This extreme material degradation left Bennett with a severe handling constraint. The factory load paths were no longer intact. Any attempt to pull the aircraft out of the mud using its original factory tow hooks or lift the wings by their designated jack points would result in the immediate and catastrophic tearing of the remaining airframe. The corroded aluminum skin simply lacked the tensile strength to support the dead weight of the waterlogged internal framework. The wreck could not be dragged or winched without causing irreparable forensic destruction to the surviving artifact. The 1981 survey successfully established the physical boundaries, verified the identity of the harvested airframe, and documented the severe degraded condition of the remaining metal. By mapping out the precise level of corrosion, Bennett was able to initiate the preliminary legal and logistical planning necessary to secure the wreckage from further destruction. Securing the historical rights and defining the footprint of the site was only the first necessary phase of the recovery operation. Moving a massive, highly compromised, and deeply corroded fuselage away from the jungle perimeter would require a highly specialized extraction geometry. In 2003, exactly 58 years after the massive aircraft was pushed off the runway, formal extraction began. Not to locate the wreck, but to stabilize what remained. Thick roots and heavy tropical vines had grown through compromised skins and open nacelles, anchoring the metal to the earth. The crew could not simply pull it free with heavy machinery. Any uncontrolled tension against that living anchor would act as a shear force, tearing brittle aluminum skin and crushing the remaining internal ribs. The team first cut and cleared every organic tie by hand, working back to the load-bearing junctions of the wings and the main fuselage. As Bennett had already established, the factory hoist points were unusable, and lifting the wing as one continuous piece risked buckling the center section under its own dead weight. The extraction geometry therefore treated the wings and the central fuselage tub as separate, supported loads. Each separated section required dedicated external support. The lift engineers utilized wide, heavy-duty slings and long structural spreader bars to distribute vertical forces across fragile surfaces, then lowered the components onto purpose-built support frames designed for transport. Rather than relying on a long, punishing road convoy, the recovery plan emphasized controlled handling and containerization. The aircraft sections were secured for coastal movement and taken by local craft and barge to the deep water port of Leh, where heavy maritime infrastructure allowed the loads to be staged and prepared for export with minimal shock and flexing. At Leh, the sections were offloaded onto hardstand inside a secured perimeter, they ending the most physically dangerous phase of the extraction and positioning the airframe for export preparation. Securing commercial maritime freight space from the port of Leh demanded rigid dimensional compliance, forcing the recovery team to manage the massive wings and fuselage as isolated structural loads for international export. The deep water infrastructure at the Papua New Guinea staging ground provided the heavy lift cranes necessary to shift the secured aircraft components from their transport cradles onto standard maritime shipping platforms. To facilitate the ocean transit, the loadmasters had to carefully lash the fragile, corroded aluminum sections onto open, flat rack containers. This method allowed the oversized wings to safely occupy standard cellular cargo hold slots without requiring custom crating, ensuring the massive artifact could be legally and safely accommodated on a modern commercial freight vessel. From the port of Leh, the wreckage entered commercial export channels, but published accounts diverge on the precise destination and chain of custody, some routing the shipment through Australia, including references to Melbourne and Victoria, while others placed the recovered sections later in New Zealand private storage. What is consistent is that the wing and fuselage structure left Papua New Guinea for a drier, regulated environment, halting the moisture-driven decay that had dominated its jungle years. The artifact, however, moved as a profoundly incomplete, engineless structure, and that absence shifted the problem from extraction to bureaucracy. Ownership, export controls, missing major components, and costs now governed what could happen next. From that point on, handling, storage, and structural support had to be designed around an airframe that no longer carried its propulsion mass. In storage, the engineless wing and fuselage sections had to sit on custom supports, and the open nacelle voids complicated any future reattachment without internal reinforcement. The transfer from the docks into covered storage completed the last major movement of the recovery effort. No single authoritative curatorial report verifies its current condition. What can be stated is the operational consequence. Once in dry, climate-controlled storage, the jungle-driven corrosion process stopped. That arrest of destruction preserves what remains, but it does not solve the separate problem of reassembly. The airframe currently exists in a strict state of preservation limbo. This condition occurs when a highly compromised structural artifact is successfully saved from the environment, but remains entirely unassembled due to immense logistical, technical, and financial barriers. Returning a rare twin-engine monoplane to a recognizable form is not merely a cosmetic undertaking. It requires the meticulous fabrication of complex internal load-bearing frameworks, the metallurgical testing of surviving components, and the exact reconstruction of the main wing spar architecture that was fundamentally weakened by continuous exposure. The engineering reality of restoring this specific airframe is strictly governed by its large physical dimensions and its severe lack of material integrity. Because the lower fuselage and wing roots suffered extensive oxidation, the original structural load paths no longer function. Any attempt to reattach the wide cantilevered wings to the central fuselage tub would require designing and machining a completely new internal support skeleton just to hold the exterior skins in proper alignment. This level of restorative engineering requires massive dedicated hangar space, heavy overhead gantry cranes, specialized aeronautical tooling, and tens of thousands of skilled man-hours. For a privately held artifact, securing the heavy capital and the specialized engineering talent required to execute a return to static display represents a massive procedural boundary. Consequently, the separated components of the aircraft remain statically supported on isolated transport jigs and locked exactly in their fragmented configuration. Because the wreckage is held within private infrastructure, highly specific data points regarding the internal condition of the airframe are completely unknown to the broader technical community. There are no published curatorial reports detailing whether the severe localized oxidation on the belly skins has been actively neutralized with chemical corrosion inhibitors, or if the decay has simply been arrested by the ambient dry air. The baseline engineering assessment, specifically what precise percentage of the original factory metal possesses enough tensile strength to bear weight in a reconstructed airframe, remains an entirely open question. Furthermore, the exact inventory of surviving internal structures, such as control cable pulleys, hydraulic reservoirs, and original cockpit instrumentation panels, is not publicly documented. The historical record confirms that the primary structural volume of the aircraft was secured, but the microscopic reality of its material health is shielded from external inspection. That lack of visibility prevents any shared, credible engineering baseline. Securing the surviving structural remnants successfully preserved the last known physical footprint of this specific high-speed reconnaissance platform. The immense physical extraction effort effectively stopped the clock on the total destruction of the machine, transitioning the technical problem from one of immediate environmental salvage to one of indefinite logistical holding. By bringing the fragile wings and fuselage out of the equatorial zone, the recovery operation successfully executed the ultimate objective of artifact retrieval. The physical components are permanently removed from the threat of total biological consumption. The Mitsubishi Dinah remains locked in a static holding space, entirely saved from the Earth but not yet returned to form.